Make sure this thing's working. All right. Dear Father, we thank you for this day. Again, I thank you for your students. Just ask you to bless our work today. Help us to glorify you. What we do, Lord. In your name I pray, Lord Jesus. Amen. Here's the attendance sheet. So I'll start it over here. Do you guys have any questions before I get into it here? All right, well, let's talk about curvilinear coordinates. Now, so generically speaking, we're going to talk about 3 dimensions, all right? So a set of curvilinear coordinates, we could think of them as like, you know, U1, U2, and U3. And those coordinate lines could be curved, right? Something like, I don't know, these could be like the U1 kind of lines, and then I probably shouldn't even hazard this picture. Here's U2, something like that, and here's where I'll get into trouble. U3, you can imagine. I can't do it I can't do it justice. The point is that if you were to look at U1 hat, it's perpendicular to U2 hat. It's perpendicular, and that's perpendicular to U3 hat. So like the lines of constant, one of these would be like U1 is changing along here, but on a given U1 line, U2 and U3 would be fixed. All right, so this is the general idea of a set of curvilinear coordinates. There are 3 functions of x, y, and z such that if you look at the levels of these functions, they kind of divide the space up into points. Now, I don't think this picture is terribly helpful. I'm going to erase it from the record. So if you didn't get it down, you didn't miss much. So primarily in here, we're interested in the particular curvilinear coordinates of either like cylindrical coordinates or spherical coordinates. All right. So we'll start with cylindrical coordinates because those are a little bit familiar, hopefully from calculus 2. So for cylindrical coordinates, if I draw a picture like this, all right, so my usual x, y, z picture, and we take a point up here, let's say x comma y comma z, right, you can drop that point, project it down here to the xy plane, right? That point projected down to the xy plane would be x comma y comma 0, right? And so down there in the xy plane, if you can imagine it, we can picture this distance right here in the xy plane, which we usually call r, all right? So, and the counterclockwise angle swept off the positive x-axis we denote by theta, right? So you know the deal. If we draw a triangle down here in the xy plane, like this, right? Then you know the deal. The hypotenuse has length r. Over here you've got r cosine theta, and here you've got r sine theta, right? And so what are the formulas that govern cylindrical coordinates? They should be familiar. X equals to r cosine theta, y equals to r sine theta. And what about the formula for z? It's a little bit kind of dumb, but the formula for z is z equals to z. So there you go. So cylindrical coordinates are just when we pair, the usual polar coordinates in the plane, all right, to 3 dimensions. And so like here are a formula for it would be the square root of x squared plus y squared. So we do insist in here that you could call this, I usually call this the polar radius. And I'm going to insist that the polar radius is non-negative. All right, so I do mean the positive root. We do some stuff in Calc 2 where we graph with like negative radius and stuff like that. You know, we identify negative radius with like the 180 degree modified angle. I don't do that in here. All right, we don't do that. So polar radius, non-negative, just the positive square root. So what is this geometrically? If you think about this, this is the distance from x, y, z to where? Well, to the z-axis, right? If you were to take this point, right, and you were to say, okay, well, what's the closest point on the z-axis, right? It's that point right there, right? 0, 0, z is the closest point to that given point. And the distance from 0, 0, z to x, y, z is the square root of x squared plus y squared, right? So that's the meaning of polar radius. Okay, so some examples. What if we have r equals to r? What is this? In cylindrical coordinates, this is what? In Calc 2, this would have been a circle centered at the origin with radius r. I'm assuming big R is a constant, right? What is this now? This is a cylinder. It's a cylinder, right? If you wanted me to convert to Cartesian equations, what would we do? What would the Cartesian equation of the cylinder be? We square both sides, right? We got r squared is equal to big R squared, which gives me x squared plus y squared equals to r squared. And I think we ran across this last class, right? That's a right circular cylinder with axis to the z-axis. All right? All right. So what if we wanted to parameterize like the cylinder like this, right? So example 2. Suppose you want to parameterize the cylinder that has 0 less than or equal to z less than or equal to 3, let's say, right? What would my parameterization of that look like? How about this? We could use r of, see, that's why I get into some trouble using r vector for parameterization here. So to avoid trouble with that, let me throw out the suggestion that we can also use a big like hourglass x for the notation for the parameterization, just so there's no ambiguity, yeah, with the other use of r. So x, and let me suggest we could use z and theta, right? And what do you guys want to let the radius of this cylinder be? Student's choice. 12. 12? All right. So what we're going to do, so the equation of this is r equals to 12. So we just put r equals to 12 and these equations right here, and that gives us the parameterization, you see? So 12 cos theta, 12 sine theta, z, right? 0 less than or equal to z less than or equal to 3, and theta ranges from what? To 0 to 2 pi, if we want a whole cylinder. What if I just wanted a quarter cylinder? What would I do? If I just want the quarter cylinder, which is sort of in like the positive octant, yeah.
0 to pi.
0 to pi over 2, but yeah. It's like if I just wanted 0 to pi over 2, in other words, I just want like this piece, right? Then I could just I could do 0 less than or equal to theta less than or equal to pi over 2, all right? So my larger point to you here is with cylindrical coordinates, we can make quick work of a cylinder by simply using the cylindrical coordinate formulas to create the parameterization. See how that works? That's a nice move. One other example here. So you guys tell me, if I have theta equals to pi over 4, what is that in cylindrical coordinates? Can you describe it geometrically for me? What do we have? Here, let me get us started. Here's a picture, x, y, z. So, yeah.
It's just like a half plane?
It's a half plane, right? Because in 2 dimensions, it would have been a ray, right? It would have been this ray at pi over 4, right? But now, we have that at every z, right? So it's a stack of rays, which, as you have rightly called, is oops, I tried, a half plane, right? And how would we find the Cartesian equation of this half plane? What is y over x equal to? The r's, they'd be canceling, and we've got tangent theta, right? So if I want to find the equation for a half plane, supposing I'm not where I'm not where tangent theta lets you down, right? There's two places where tangent theta fails. Where there's division by 0 for cosine, right? So namely plus or minus pi over 2. Those are out of bounds. But setting those cases aside, this will do it for us. What's tangent pi over 4? It's 1, right? So the equation here is y equals to x. That's the equation of the half plane. But there's got to be another, that's not a half plane, is it? That's a whole plane, isn't it? If I rewrite it if I write it more suggestively like this, x minus y plus 0 times z, just to kind of be really, really manifest about it. What's the normal to the plane? 1 minus 1, what? 0, right? So that would be the normal to this half plane. Of course, you could go plus or minus that, right? Depending on whether you want to think of it pointing this way or back that way. But I think to make it the half plane, we need to add an inequality, right? Which would be what? How about this? How about x greater than 0 should do just fine? I would say, technically speaking, the z-axis is not part of this, right? Because the angle is not really defined at the origin, is it? What angle is the origin at? We don't define that. So, nevertheless, hypocritically, we're going to use polar coordinates on contexts which include the origin. What's up with that? The answer, yeah, I know, right? Exactly. So the answer is that we're doing integration eventually, and so integration doesn't care if there's like just one point missing. Unless that point happens to be divergent, right? In which case you need to approach it in a limiting sense. But thankfully, the places where we run into this, for the most part, they're not really improper integrations. They're more of a, just like a sort of a jump discontinuity or something, which doesn't really affect the integration. All right. So, a usual question, example 4, I'll give you one. Let's suppose we have the point which is 3, 7, minus 4. Find cylindrical coordinates. Cylindrical coordinates. So I'll get us started. R, square root of 3 squared plus 7 squared, also known as the square root of 58. All right. And of course, z, I'll do that one. Minus 4, right? What's the theta? And to make things more interesting, let me level this up a bit. I'm going to slap a minus on here to trip us up, because we need practice with that always.
Inverse cosine of
Ooh, inverse cosine.
x over r.
Interesting.
Or none.
Maybe. I don't know. I had to draw a picture. So like you're saying minus 3 7's like over here somewhere, right? And you're saying inverse cosine will get it?
R over.
I think, well, man, does inverse cosine work there? I need to teach trigonometry again. Inverse cosine goes from like 0 to pi. Yeah, it should work there. Yeah. So your point is x is equal to r cos theta.
Yeah, and then divide by r.
So yeah, theta is inverse cosine x over r. Cool. So your theta inverse cosine of minus 3 over the square root of 58, right? This is not how I usually do it. And that's fine. You don't have to do what I do. Just do something correct, right? And show your work so that if you're incorrect, I can still give you something. Let's see here. Inverse cosine of minus 3 divided by the square root of 58. All right, what we got here? I'm in degree mode, that's good. I mean, sometimes we need to be in radian mode, but I'm in degree mode here for a moment, which is, I think, helpful. Because at least I can visualize this more readily. 113.2 approximately degrees. And that, I think that checks with, yeah. So what's the other way you could have done this? How about what's the inverse tangent of, you know, like 7 over 3, for instance? Forget about the minus for a second. So that gives me 66.8 degrees, right? And so I know what that means, right? That's like, that's the reference angle off the negative. Ah, come on. That would be this angle over here, right? So if I know that and I understand this picture, then I can also find my way to 113.2 by subtracting 66.8 from 180. That's what I tend to do. I don't care what you do, as long as you can find, you know, standard angles correctly. Just remember, we can't just use inverse tangent of y over x when x is negative, right? It'll let you down. And in quadrant 3, there is no sine or cosine or inverse. I mean, none of the inverse functions work in quadrant 3, right? So like this inverse cosine thing works in quadrants 1 and 2, yay. Inverse tangent will work in quadrants 1 and 4, fine. Quadrant 3, you're on your own. You got to think geometrically. Or you can remember the 4-case formula for the angle from Wikipedia, but I don't recommend that. It's better just to think about these things geometrically. Okay, so far, so good. So there you go. That's the polar coordinates. I think technically speaking, I should really put it in radians for polar coordinates in my estimation, but I'm not going to be a jerk about that. If I ask you for polar coordinates and you give me in degrees, I just think degrees and radians are two different ways to describe the same coordinate, really. All right. All right, so here's the weird new thing. You can also think about the polar coordinate frame, or rather cylindrical coordinate frame. Now a frame is a set of 3 vector fields, which for us is going to have length 1, and they're going to be perpendicular. It's going to be a so-called right-handed frame. And so the way this works here is r hat, I think theta hat, and then z hat. So if I can picture some of these, like, all right, so if I take that's supposed to be the unit circle in the xy plane, all right? R hat points radially outward. So I'll only draw it here and here because otherwise my picture gets kind of fussy. But R hat points, listen, if I draw the z-axis coming out at you, all right, then R hat points like this. It points radially out. Now it doesn't have to be based on the z-axis, mind you. It points, it's a length 1 vector that points away from the z-axis with length 1. So what r hat is, it's a unit vector of length 1 that points in the direction of increasing r. I'll repeat that. R hat is a unit vector, really a unit vector field. Let me write this down. So it's a unit vector field which points in direction of increasing r. Now, if we go back to our experience last week, we talked about x hat, y hat, z hat, right? And if you think about it, x hat, 1, 0, 0, right? Z hat, my bad, y hat, 0, 1, 0. Z hat, 0, 0, 1. What are these? If I draw a picture of those in 3 dimensions, they're kind of boring. It's just the same vector everywhere. You pick a point in 3-dimensional space, x hat goes 1 over in the x, y hat goes 1 over in the y, z hat goes 1 up in the z. But they're the same vectors that we're attaching to every point. So it's a constant vector field. They're kind of, you take them for granted. This is very different. R hat is different at different points. So it's an honest to goodness vector field in the sense that it's variable. And I would point out that, to be fussy, I would say that we don't define r hat on the z-axis. Which directions should r hat point on the z-axis? I don't know. So I don't define r hat on the z-axis, right? But everywhere except the z-axis, you can kind of picture it. And here's the formula for it, yeah? So the formula for r hat is cosine theta, sine theta, 0. In other words, you can get it from putting r equals to 1 in the cylindrical coordinate formulas, yeah? Now theta hat, I'll picture. Theta hat, if this is the positive z coming out of this, theta hat is always 90 degrees from r hat, and it's pointing in the counterclockwise sense as you go around, all right? So here I'm plotting some theta hats from above. If I'm so foolish as to draw it in 3 dimensions, the theta hat looks like this. All right, and it goes into the board there, like that. Theta hat, I don't know, maybe you should, I have trouble drawing it here, okay? But it should be pointing in the direction of increasing theta. Everyone agrees, increasing theta on the positive x-axis looks like that, yeah? And increasing theta on the negative, on the positive y-axis, it's directly back in the negative x-axis direction if you think about it, right? So it's perpendicular to r hat, all right? So we want r hat dot theta hat to be 0. The formula for theta hat, after a moment's introspection, is minus sine theta, comma cosine theta, 0. And if you check it, this formula right here works for what I'm claiming. If you look at it, when theta is 0, right? For example, when theta is 0, we get 0, 1, 0, which is what theta hat is, right? Theta hat in this picture right here would be y hat. This theta, I mean to be minus x hat, by the way. That one up there. So theta, much like r hat, it's varying from point to point. But it's always, wherever you're thinking about it, pointing in the direction of increasing theta. All right? Now I've got good news about z hat. You already know it. All right, so the z hat in cylindrical coordinates is the same as the z hat over there. And if I was, and I mean, I can draw this picture. What is, what do x, y, and z hat look like? So like here's your x hats, right? Y hat, I drew those too close. Here, I'll fix it. Y hat looks like this. So I'm just using some color coding to save myself. And of course z hat, and I think of all 3 of these as being attached to a given point in discussion, all right? Because we're talking about how to build a vector at that point from the frame, all right? So like, so this is z hat, all right? That was supposed to be length. This is supposed to be the same length as the other ones. I'll try. There we go. Of course, you guys know x hat cross y hat is what? Z hat, right? So if you think about the deal with the cylindrical frame, I'll pick this point because it's most easy to think about. So this point right here, we have r hat goes like this, right? We have theta hat goes like that. All right, And if I do r hat crossed into theta hat, z hat. Oh man, colors. Yowzers. So it isn't true, in fact true, that r hat crossed with theta hat is z hat. By the way, this automatically implies, through the magic of vector algebra, that theta hat crossed with z hat is equal to r hat, and also that z hat crossed with r hat is equal to theta hat. So the same patterns that hold for x and y and z hold for r, theta, and z. If the first one's true, the next two automatically follow. You can prove it from like that back cab identity. Now, listen, let me draw another picture here. So like here is the other place I can draw it decently, sort of. So here's my r, right? Theta points into the board there. And think about it again. R hat crossed into theta hat, z hat. So it doesn't happen at just that one point. It happens everywhere. All right, and that's part of why we would say that. So like this is part and parcel of what I mean by saying r theta z is a right-handed ortholinear coordinate system. When we talk about an ortholinear coordinate system, what I mean by that is that the unit vectors to the coordinates meet at right angles, right? And right-handed means that if I look at the first two coordinates, I take the cross product of their unit vectors, I get the third. Like x, y, z is a right-handed coordinate system because x hat cross y hat is z hat. On the other hand, if I was to talk about the y, x, z coordinate system, that would not be a right-handed coordinate system because y hat cross x hat is not z hat. So like if you were, and I don't know why you do this, but so x, y, z, right-handed. But guess what? If we were to do, for whatever reason, y, x, z, this would be left-handed, which is of course an evil inferior type of coordinate system that we don't consider. Sorry if you're left-handed, but you know, the math community has spoken. We confer right-handed. We have a right-handed cross product, right? There's a different cross product you could define with your left hand, like A cross B gives you A cross B, but that would have been minus the cross product that we defined, which would have been an equally like logical choice that would be inferior because it's based on left-handedness. Are we okay? Yeah. I'm probably joking. Probably. Where was I? All right, so next up, we should talk about the more interesting thing, which is spherical coordinates. So, I mean, cylindrical coordinates, I don't think they're much. There's not like a lot of daylight between cylindrical coordinates and what you've already done in like Calc 2, right? Because we're just tacking a z on, right? But the spherical coordinates, well, that's something a little bit more adventurous. And so let's introduce those. And to be clear, this is the math version. That is relevant to me because I am currently teaching another course right now called Electromagnetics, where we use the physics version of spherical coordinates, which uses two of the same letters with an opposite meaning, which is super fun for me this semester. So if at any point I flip the meaning of the angles here, just know that it's the fault of the other course and no shortcoming of my own. So, sorry, I'm an idiot. So here's x, y, my bad, x, y, and z. All right. So as usual, we start by thinking about a point out here in space, x, y, z, and we want to describe what are the spherical coordinates of this point. So the way we do this is we think about the distance to the origin. All right, and we're going to call that rho. So the distance to the origin rho is, of course, by definition, the square root of x squared plus y squared plus z squared. Once more, we are insisting on taking the positive root. I don't think about negative rho, and neither shall you. I mean, I guess I can't compel you not to think about it. That's not the way like freedom of conscience works and stuff. Just rest assured there will be negative social pressure for using that concept in this class. Okay, so then we drop this point down to here to the projection in the xy plane, namely xy 0, right? And we once more think about the distance from the origin to that point in the xy plane. This is, of course, well, it's r, right? Okay, so there are two angles in spherical coordinates. And those two angles are theta, which we already know, right? The angle from polar coordinates, theta. And then the angle from the positive z-axis down here, like this, which we'll call phi. Sometimes phi is referred to as the polar angle because it's measured off the pole. Sometimes theta is called the polar angle because it resembles the angle from polar coordinates. You can see there's room for confusion here. So I will be very unsophisticated and merely refer to them as theta and phi to avoid this. But they are very different. Theta ranges from 0 to 2 pi. But phi sweeps from the z-axis, which is phi equals to 0, down all the way. And it doesn't need to go past there. All right, so phi is just going to range from 0 to pi. Some people have also proposed calling phi the colatitude, since it's kind of like the latitude for, like, you know, coordinates on the Earth. So yeah. Now let me finish this thought here. What are the formulas that define spherical coordinates? Well, if you look at this purple triangle down here, right angle there. So this is what? This is, if this is r, then of course over here we've got our sine theta, right? And over here we've got our cosine theta. Leave yourself some room to write there. But what is r equal to in this picture, by the way? Notice that by alternate interior angles, there's parallel lines here, right? Whee! And so that's also phi over here. If you use tilt your head and squint, it's there. And as such, this is also a right triangle. And so the hypotenuse is rho, this is the opposite. So what you're up against here is rho sine phi, right? And also, by the way, this is rho cosine phi. If you're wondering, this is RHO, quote unquote. Whereas this is PHI, and well, you know what theta is. So anyway. So, all right, so the formulas then are x is equal to rho. So notice that r is actually rho sine phi, so we've got rho cosine theta sine phi, and down here we've got rho sine theta sine phi. So putting it all together, we've got x is equal to rho cosine theta sine phi, y is equal to rho sine theta sine phi, and z is equal to rho cosine phi. So there you go. These are the spherical, these define the spherical coordinates rho phi theta, I think. So let me jump over to the spherical coordinate frame before I forget. So if I pick a particular point, I like this point. So rho hat points radially out from the origin, like that. Theta hat, we already know the deal. Same theta hat as before. So like this. All right. Now phi hat, where does it go? So like so phi swings like this, swinging down. So here, the direction of increasing phi is straight down there. So at this point on the positive x-axis, phi hat's actually like minus z hat, and theta hat, for what it's worth, is actually y hat, and rho hat is actually x hat at this particular point. Those are not generally true, but they're true at that specific point. So what's the relation between rho, phi, and theta? Well, you can see from this, of course, that rho hat crossed with theta hat. Oh, wait a minute. Well, that's minus z hat. That's not what I want. But how about rho hat crossed into phi hat is theta hat, right? So for this reason, I like to refer to the rho phi theta coordinate system. So to put things in order, we do rho, then phi, then theta. That makes it a right-handed coordinate system. I have some more pictures to show you, but before I get back into the, I mean, I haven't written down formulas for rho hat and theta hat. I mean, you already know the formula for theta hat. It's the same one I showed you just a minute ago for the cylindrical coordinates, right? So like, I guess I can tell you, rho hat, well, theta hat, phi hat is a little bit complicated. Theta hat is still minus sine theta, cosine theta 0. Rho hat, if you want to think about it, if I were to picture rho hat, it's radially out from the origin in every different direction all at once. And so to get the formula for it, all you got to do is put rho equal to 1, and that gives you a vector that points from the origin, right? If you think about like the unit sphere, if I have this point like that, right? If I move that vector out to here, that's what I would call rho hat. So that vector from the origin to there, I can get just from putting rho equal to 1 in these formulas. And as such, rho hat, we can understand geometrically as simply cosine theta, sine phi, sine theta, sine phi, and cosine phi. Now the phi hat, I don't remember off the top of my head. I always have to look that up. All right, but okay. So we'll get back to the phi hat when I get the projector out here in about 3 minutes. Until I do that, though, I want to derive for you guys the parameterization of the sphere. Now that we have spherical coordinates, it becomes a simple matter. Like, what is the equation for a sphere in spherical coordinates? At the origin, right? The sphere centered at the origin. So suppose we've got a sphere of radius r, right? Centered at the origin. What's the equation for such a sphere in spherical coordinates?
Rho equals r.
Rho equals r. There you go. It's almost too easy. So there you go. That's the equation for a sphere in spherical coordinates. Now that is equivalent to like the square root of x squared plus y squared plus z squared equals to what? Equals to r. Or if you square both sides, that's what it looks like in Cartesian variables, right? So the equation of a sphere, the sphere of radius r centered at the origin, simply x squared plus y squared plus z squared equals to r squared. What is the parameterization of the sphere? Well, if we use phi and theta as parameters, it's as simple as going over to the defining equations and putting r for rho. R cosine theta sine phi, r sine theta sine phi, and finally r cosine phi. There you go. That is a parameterization for the sphere that we will learn later is a much more friendly thing for actually calculating things on a sphere when we get to that. Some of this stuff we're not going to use for a while, guys, so I'm just kind of like introducing you, and we'll come back to this later. You have a little bit of homework on it right now, but nothing too terribly deep. We'll learn how to derive many of the things I'm claiming geometrically using calculus as we go on, which I think is really cool because some of these things you may or may not see, but we can derive them with calculus. So let's see here. You guys know what theta equals to a constant is. It's a half plane, right? That's still true here. What would phi equals to a constant, right? Like, is this example 5, 6? I can't. I've lost track. What if I have like phi equals to, you know, pi over 6? What would that be? I mean, I can write down the equations, right? We've got x is equal to rho. Is it sine theta? Yeah, sine theta cosine pi over 6. Oh, I've already forgotten my equations. Goodness gracious. Cosine theta. Don't let me do that. Cosine theta sine of pi over 6, right? Y is equal to rho sine theta cosine, my bad, sine pi over 6. Good grief. Z is equal to rho cosine of pi over 6. Of course, we don't need our calculator. We know these, right? So you've got 1/2 rho cosine theta, 1/2 rho sine theta, and finally here, root 3 over 2 rho. And so, by the way, if we were to write down x of, let's say, rho theta equals to rho cosine theta over 2 rho sine theta over 2 root 3 rho over 2, guess what? This parameterizes cone. Oh, I didn't tell you it was a cone yet, did I? But this is a cone. If you think about it geometrically, that should be somewhat evident. See, because we're talking about all points that have angle, pi over 6 off the positive z-axis. Well, that's a cone, right? And well, how do you parameterize a cone? Just like that. Those are the parametric equations for a cone for x, y, and z respective. What if you wanted the vectors which were normal to the cone? What would those be? Like this, my friends, is phi hat. So phi hat provides the natural normal to the cone. That half plane, the normal to it, theta hat. The sphere, the normal to the sphere, guess what? Rho hat. Rho hat points normal to the... So if we look at a surface of constant rho, rho hat points normal to that. Surface of constant phi, phi hat points normal to that. Right. So as we study surfaces, these cylindrical and spherical frames are actually very helpful. Now, this is not in the usual calculus book, like it's not in Stewart, and that's unfortunate because it deprives you of a much easier way of doing things, actually. However, the spherical coordinate frame is something you will see in a good engineering book, certainly in a good physics book. Like most of the Calculus 3 that's done in application is done with spherical or cylindrical frames. So, once I get this thing working. So your homework is collected tomorrow, yes? Yeah. Trying to think. Oh, one of you made a correction to a previous lecture. I had said that R of I had said that like R of 1, 1 was P plus Q plus R, but actually that's bogus. It's actually Q plus R minus P relative to our discussion, because there were 2 minus P's, and I was somehow making 2 minus P's going into a plus P, which, because 1 P canceled or something. Anyway, it was wrong. It's supposed to be minus P there, if you look back at that example. It was around where we introduced the parameterization of like a plane. Uh-oh. Oh, there we go. All right. Well, I thought I plugged this thing in. Oh, funny thing. If you don't plug the monitor cable in, it's hard to get it projecting. All right, so in my notes, I give a much more abstract definition of like a surface in n dimensions. That doesn't really matter to you guys too much, but it's just there for your amusement. We can define parameterization in higher dimensions like that. What I wanted to play around a little bit with you is just these. So like here's part of a hemisphere. And I think if you look at these formulas now, maybe you'll understand where they're coming from, right? This is just like spherical coordinates with u playing the role of theta and v playing the role of phi. And that's why I'm letting u range from 0 to 2 pi, but phi is only going from 0 to pi. Wait a minute, what? Dude. Oh, wait a minute, down here. 0 to 3 pi over 2. So that sweeps like around 3/4 of the circle, and then here 0 to pi over 2 just gets me, if you look at z, the z formula here, look, cosine is positive going from 0 to pi over 2, so this is only allowing positive outputs for z. If I let this v range further, like from pi over 2 to pi, that would pick up the part where cosine is negative, and that would pick the bottom half. So we can manipulate the part of the thing we're parameterizing by judicious selection of parameters if we understand the formulas. That's not calculus 3, though. Oh, the double scrolling. My nemesis, the double scrolling. So, so here's some pictures which are worth looking at. This is a plane cut off by the coordinate axes, so whatever. Here's a more lower tech picture of a family of planes. All right. This one, there's a single equation which will define this surface that has 1, 2, 3, 4 holes. Like a trefoil knot or something, I forget. I don't remember the formula for that right offhand. Of course, this is a rather boring picture of a ellipsoid. So if you have something of the form, x squared over a squared plus y squared b squared plus z squared plus c squared like that equal to 1, that gives you, if a and b and c are also 1, then that gives us the unit sphere. These are called quadratic surfaces. If we have like a sum of squares, sum or difference of squares, then we get different quadratic surfaces. So like the ellipsoids are some of them. These are interesting. If you have x squared plus y squared minus z squared, depending on what you set that equal to, you either get a hyperbolate of 2 sheets like here, or you see how it's pinching down? And then once you get past a certain point, you get a hyperbolate of 1 sheet. All right? And the wireframe thing here is actually the case that we have equals to 0. Equals to 0 is a cone. So like between the hyperbolate of 2 sheets and 1 sheet is the cone. If you look in my zoo in the website, you'll see I have those animated going from one to the other. But, so here's ellipsoid. Come on. Man, I said go to the next page. I dare not do the double scrolling. Here's an elliptic paraboloid. Down here we have a hyperbolic paraboloid and the equation. All right, so we'll talk more about how to understand what you're looking at in terms of like specializing what are called traces and such, but we don't need to do that yet. We'll do that when we get to integration, which is when we have to do these things more completely. What I really wanted to show you, yeah, feel free to pack up, we're almost done here, is at the end of this, I actually have pictures of the frames. I will eventually get to the pictures of the frames. So, by the way, there's the missing formula for phi hat. There it is in all its glory. If it's right, the dot product of this and the above and below should be 0. And that's on page 81. Oh man, I'm sorry, I was teasing you. I guess it's much later. Here's pictures. If you look over to like page 177, here's pictures of the R hat, theta hat, and if you're so foolish as to attempt such a thing, Z hat. Well, Z hat's easy, but here's pictures of rho hat. Here's pictures of theta hat. And here's a picture of phi hat as it like wraps down off the z-axis if you want to try to picture. I don't try to draw these pictures. But anyway, thanks guys. I was about to say have a good weekend, but it feels like that's backwards.